Okay, now we will be discussing two problems related to capacitors with dielectrics. One is the example problem, and the next one will be a problem from questions at the end of the chapter. So, first discussing example 26.6. A parallel plate capacitor has plate of dimensions 2 centimeter by 3 centimeters, separated by a 1 millimeter thickness of paper. We have to find these two things. A is find its capacitance and B is what is the maximum charge that can be placed on the capacitor. So first we have to write down the data. So the data will be first the area. It's given that the plate is of dimension 2 centimeter by 3 centimeters. So 2 into 3 will give us the area of the plate, that is 6 centimeter square, and we have to convert the centimeter into meter square. So by converting that, I'll be getting 6 into 10 raised to the power minus 4 meter square. D is the distance between the plates, which is 1 millimeter, and you know that milli is 10 to the power minus 3. So 1 into 10 to the power minus 3 meters now. Kappa for paper is 3.7. It's a constant, so it will be given, although it's not given in the question, but these constants are given at the end of the paper, or if you are given a quiz, then will be given in the quiz. And epsilon naught is again a constant whose value is 8.8 into 10 to the power minus 12 coulomb square per Newton meter square. So what we have to find in part A is the capacitance. So we will proceed as we know the formula for capacitance for parallel plate capacitors. It is C equals to kappa epsilon naught A over D. We know the value of epsilon, we know the value of kappa, we know the value of area, and we also know the value of D. So by putting all these values within the formula, we will get 20 into 10 raised to the power minus 12 farads. Minus 12 is pico, so I can simply write it as 20 picofarads. So this is the solution for part A. Now for part B, we have to find the maximum charge that can be placed on the capacitor. So we have to find Q. Again, this E for paper will be given because it's a constant, and its value is given according to the dielectric used. So we know the value of E, we know the value of D. Easily we can find V over here. V is equal to ED. So by putting this V and the C we have calculated in part A, we can find Q. So Q is equal to C delta V, which is equal to the value of C, the value of V, and in the end we get 0.32 into 10 raised to the power minus 6 coulombs, which is equal to 0.32 microcoulombs. So this is a very simple problem, and it can be easily done if you know these basic formulas. Now moving on to problem 44. Okay, now we will be discussing problem 26.44. You can find this problem at the end of the chapter under section 26.5, and the problem number is 24. The problem says that how much charge can be placed on a capacitor with air between the plates. So if we are using air over here, it means that the dielectric between these capacitor is air, the plates before it breaks down. So we have to find the maximum charge that will be stored on the parallel plate capacitor when we have air as dielectric between them. If the area of each of the plate is 5 centimeter square, now area of the plate is given. The B part is, what if the maximum charge if polystyrene is used between the plates instead of air. So we will be replacing air with polystyrene. So the solution for part A will be, first we have to write down the data. Um, Kappa for air is 1, and from the table we can find the electric field when we are using air as dielectric, and the value of E is 3 into 10 raised to the power 6 volt per meter. Area of the plates is given, that is 5 into 10 5 centimeter square. So we'll convert it into meter square, which is 5 into 10 to the power minus 4. Now I am interested in calculating the maximum charge before it breaks down. So I know that Q is equal to C delta V, and also I know that C is equal to A epsilon K over D, and V is equal to ED. Because I have to calculate Q, for that I must know C, I must know delta V. Therefore, I can find Q equals to, by putting the value of this C over here and V over here, and I'll simplify it. D cancel out हो जाएगा, and I am left with Q equals to A epsilon kappa E. So I know the value of A, I know the value of epsilon naught, I know K and E. So simply uh, by multiplying all these values, I'll get 13.3 into 10 to the power minus 9 coulombs, which is nanocoulombs. So I'll write Q equals to 13.3, and C, N is for nano over here. Now for part B, I'll replace this air with polystyrene. So the kappa of polystyrene will be given, and then according to that kappa, you know the value of E. So the value of kappa for polystyrene is 2.56, and accordingly E is 24 into 10 raised to the power 6 volts per meter. So simply Q, from here we know that A epsilon kappa E. Just fill in the values and you'll get 272 into 10 to the power minus 9 coulombs. Again, minus 9 is nano, so 272 nano coulombs. So this is it. So it is very easy to solve a problem if you write down the data first, and then you can easily see what the equation will be if you know the main data points in the problem.